the issue with dense networks is that it doesn't respect the spatial properties of images. So this type of network is also known as the multi-layer perceptron, and it has this topology that in which each layer uses all input data from the previous layer in order to produce a single outcome. Because of that, I mentioned before, it is called dense or fully connected layer. And but as you can see here, it considers all pixels of the image similarly when performing the linear transformation. It doesn't consider that a pixel, for example, is centered at some region and that it has neighbors respecting vertical and diagonal and horizontal directions. So this is why convolutional neural networks were developed. A convolutional neural network has layers that are responsible for performing convolutions with the input image with filters that are going to be learned, not defined manually as we did in our lectures about filtering, image filtering. And now we have new terminology to describe. A convolutional layer is a neural network layer, but instead of have dense units, it has convolutional filters. Pooling, which is a layer that decreases the size of the output. Feature maps, or also activation maps. I'm going to describe that later, but this basically is the result of a convolutional layer and a fully connected or dense layer. This, as I'm showing you here in this slide, is a convolutional neural network architecture. Those are also called CNNs. So C stands for convolutional and NN for neural network. And it is known as the Linnet architecture. I mentioned it in the first video. This was an architecture proposed for the purpose of digital recognition, and it has, in this case, 2 convolutional layers, 2 pooling layers, and then, in this case, 3 fully connected layers. And we are going to describe that. So first, the convolutional layer. When we have an input image, let's say this image has 32 by 32 pixels by 3, in this case it's an RGB image, we are going to have a neuron as a filter. This filter has size P, Q, D, let's say 5 by 5 by 3. Remember from the lectures about image filtering, we defined, for example, a 5 by 5 Gaussian filter or mean filter or median filter that would process the input image and produce an output image that was modified by that filter, right? In this case, it is exactly the same. So, but each neuron will define a different filter. Which filter exactly? It is this like a Sobel filter for edge map extraction? It is a Gaussian filter? Is it a least square filtering? No, it is none of them. It is actually, it begins as a random filter, the same way we had in the dense layers. So we begin by defining it randomly, and the network will learn the filter, the values of the filter. So in this case we have, for example, 5 by 5 filter. Why it has 3 also? Why it has the third dimension, not only 5 by 5? Because it processes, in this case, an RGB image. And then it is not a grayscale image. It will compose all neighbors, 5 by 5 neighbors, but also considering R, G, and B pixels at the same time. So each neuron or filter performs a convolution with the input image, and that is centered at a specific filter, a specific pixel. So mathematically, we have for each pixel the same equation that we have for dense layers. However, in here we process it differently because remember, convolutions work or operate locally, not globally. A convolution filter only operates on all pixels if the size of the filter is the same size of the image, which often is not the case. So if we define a convolutional layer with 10 filters or 10 neurons, the output is going to be 10 images. Those images are called feature maps. So we have a input image 32 by 32 by 3, and then the convolutional layer has 10 filters of 5 by 5 by 3. That means for each pixel of this image I produce a single value here. And then because I have 10 filters, I have it the same image but filtered using 10 different filters. That means 10 different images. I just illustrate those in different colors here. Those feature maps are found by after an application of an activation function. Often ReLU is used. And when I stack those 10 matrices, what I have is a tensor. I'm going to detail that later. So let us talk about a concept called local receptive field. Actually, we already have seen that, but I want to recall this concept. So the input image, let's say we have this input image here, and I'm exaggerating the size of the filter just to make it easier to explain. So if I have let's say we have one filter here on the top here. We don't have values here. It's a generic filter. It is used to perform convolution with this image, input image here. If I'm processing just this pixel, the central pixel here, this central pixel will be influenced by all those neighbors. And then the pixel here, the exact pixel here, will be then a linear combination of all neighbors in this region. So this is what we call local receptive field, the region from which that pixel was originated. So the output pixel here actually originated from a region of pixels, a local receptive field. So if we apply the same concept for n filters, what we have is n feature maps, in which if we fix the pixel, pixel I, we have different pixels I, output pixels, that have the same local receptive field, but were processed differently. So let us stack two convolutional layers. Let's say we have a 32 by 32 by 3 input image, RGB image. So if we have this cat here in color, we can split this into three matrices, R, G, and B. And then the first convolutional layer, if I define that the filters have size 5 by 5, those actually have size 5 by 5 by 3, because I have one weight per color channel. So R goes to this, G and B. For every pixel, or for every filter, what I have as output actually is a feature map. Feature map is basically another image. Remember, when I use a filter to perform convolution with the image, what I have as output is another image. in this case, a 32 by 32 image. Well, but what about the padding that we require? Well, supposedly we are using 0 padding in order for the image to be processed. Then I padded all images and then perform the convolution. The output would be a 32 by 32 image. Filter it again, another 32 by 32 image. Filter it with another one, another 32 by 32 image, and so on. In the end, I'm going to have a 32 by 32 by 4 tensor. It is called tensor because it's an extrapolation of the matrix concept, in which every pixel is represented by a vector. Now, because I want to use this output to be the input of a next layer, the next layer, let's say the next convolutional layer is composed of 3 by 3 filters. But 3 by 3 is not sufficient. I have to define it as 3 by 3 by 4, because now I have 4 matrices to operate. And then finally, the output, if I define 5 filters, the result of this layer is 5 feature maps, 5 matrices. So note that in this case I'm not actually decreasing the dimensionality of the input. I'm increasing it. I'm finding new images that for which with those images, processed images, I will make the classification step easier. What I'm basically doing, I can interpret it as pre-processing the image. I'm finding different versions of the input image so that those versions are easier to be classified. As I said, in practice, 0 padding is used to avoid losing borders. If I have, let's say, a small image 10 by 10 and a filter size of 5 by 5, I have to 0 pad it by 2, so I have actually to make a 14 by 14 image and then apply the filter to have an output of 10 by 10. Otherwise I will lose 2 pixels and end up with a output of 8 by 8, so I have to be careful to be aware of that, so I have to care about that. As a general rule, a 0 padding size to preserve the image size is p minus 1 over 2, so the size of the filter minus 1 over 2. If I have 32 by 32 image with p equals to 5 and 0 padding z equals to 2, then the output size will be 32. So I can just compute that. When I design a convolutional layer, I must then take into account 3 parameters. The input size, so the how is the input size of the image or the feature map that layer receives. This is fixed, so this is defined by the output of the previous layer or the input image. The filter size, I can define the filter size, but the depth must match that of the input, remember? So I can use here filters 5 by 5 or 3 by 3 or 7 by 7, but the final number is by 3 because the input image is RGB. And the width and the height affects the local receptive field. So the larger the filter is, the larger is the local receptive field. But I don't want to exaggerate that, because by using many layers, I increase the size of the local receptive field. Okay, so don't worry about having a local receptive field that is too large. And also a convolution stride or step. On the regular convolution, stride is 1. That means all pixels are going to be filtered. but I can skip skip pixels. Let's say every pixel I process, I skip one. In this case, what I'm doing is basically reducing the size of the output. So if I have a 10 by 10 image and use stride of 2, that means I skip one pixel for every pixel that I process. Then in the end I will have a 5 by 5 matrix. Let us see a an illustration that is not a realistic one, but is a way to see how convolutional layers operate. Now I operate locally, so every filter is going to specialize in a spatial local property of the image. Let us say that I want to recognize the digit 7. Supposedly, when I train a convolutional layer, let's say with 6 different filters, each filter will specialize in this case I'm using the terminator of the digit, a middle part of the digit that is kind of diagonal, a middle part of the digit that is vertical, a L shape or corner, a horizontal line, and a terminator of a horizontal terminator. So in this way, I'm kind of splitting the image into components, in spatial components. Those are going to be combined by other filters in the next layer, so that when I note that I have horizontal, diagonal, and vertical components in this order, I have the 7 digit. So each neuron is going to be specialized in specific patterns, and it can share those patterns between classes. For example, with the class 9, I would have similar patterns. However, on the top, instead of having just horizontal and terminators, I'm going to have a loop, so something that is closed and then will differ from the pattern 7. Another thing that's interesting to observe is the number of parameters of such network. In a convolutional layer, the number of parameters is defined by the size of the filters and the number of the filters. Let's say we have an input 30, so we always have the size of the filter times d, which is the depth, the number of filters k, and plus 1, which is the bias term. So I forgot to mention, but every convolution is not just a regular convolution, it has also a bias term that is summed to all pixels or to all values here equally. So for example, if you have an image input 32 by 32 by 3 and a first convolution with 5 by 5 filters, so 8 filters with size 5 by 5, the second one 16 filters 5 by 5, and the third one 32 filters 1 by 1. So what we have, the number of parameters of the convolutional layer 1 is 5 by 5 by 3 plus 1, which is the bias, times 8 neurons, 608 parameters to be trained or to be adapted during training. The second layer, 5 by 5 by 8. Why is 8? Because we have 8 neurons on the previous one, so 8 matrices to process, plus 1, which is the bias, times 16 filters. So 3,200 and something. And the third layer has 1 by 1 filters, and you can imagine what is an effect of a 1 by 1 convolutional filter. Actually is 1 by 16. So what those filters are doing is basically they are combining the 16 matrices. So for every pixel I'm combining the 16 different matrices in the depth. So considering all of them, imagine if it was in the first, if this was happening in the first layer, what I'm doing is basically creating an image in which every pixel is the combination of R, G, and B. And then because I have 32 filters, we will have 544 weights. If we compare that with dense layers, this is much smaller. Let's say we have a 32 by 32 by 3 image. So if we do like a quick count, this image has 3072 pixels, right? So 3000 pixels, let's say. With a dense layer of 8 values, I'm going to have to learn those 3000 weights for those 3000 pixels individually and 8 neurons. That only in the first layer I would have 24,000 different parameters to learn. So this is also an advantage of using convolutional layers. They usually require much less parameters to be trained. Last one that I'm going to mention in this video is the pooling layer. The pooling layer operates over the feature map, so usually is applied over the output of a convolutional layer. And then the intention here is make the data smaller in width and height. For example, max pooling is basically a technique for subsampling using the maximum value of the pixel in a region. If I use a downsampling factor of 2 and stride of 2, I have this type of effect here. So I'm dividing the image into 2 by 2 regions and then taking the maximum value to be the output. So if I have a 32 by 32 image and use max pooling with a factor of 2, then I take the maximum of 2 by 2 here, which is 21, and then copy here. The maximum here, which is 210, copy here. The maximum here, which is 255, the maximum here, which is 70, and then copy here. If I have multiple feature maps, I keep them, so I process every one of the layers of the channels independently in this case. So the depth doesn't change, just the lateral resolution of the feature maps. Instead of using max pooling, average pooling is also a common choice. This same effect, as I told you before, can be obtained by using convolutional layers with larger strides. The effect of the pooling layer is that by reducing the image size, we allow one filter to operate in a larger region, perform a kind of multi-resolution processing. So if I have a 5 by 5 filter, but I'm processing a large image, let's say an image with 128 by 128 pixels, a 5 by 5 filter will be capable of covering, let's say, an eye of the person here. But if I reduce the size of the image and keep the size of the filter, this, instead of just covering the iris of that eye, it covers all the eye and maybe the eyebrows as well. If I decrease it further to 32 by 32, I'm covering part of the nose and also other parts that are around the eye. And with 16 by 16, I'm covering basically half or 1/4 of the face. So this will help, and also will help decreasing the number of parameters required for training, and then progressively diminishing the dimensionality of the data that I'm working with. So putting everything together, we have convolutional layers, followed by activation layers, which are often rectified linear units. I mentioned it before. It just removes negative values, and then followed by pooling, which is often max pooling. So in this architecture here, the LeNet architecture, the first layer is a convolution. It has 6 filters that, as you can see here, they don't use zero padding, so the resulting feature maps are 28 by 28. Oh, sorry, I just zoomed it too much. So 6 filters resulting in 28 by 28 feature maps. The second one is a subsampling, is a pooling layer, reducing it with the factor of 2. So now I have 6 feature maps, 14 by 14. I perform yet another convolution with 5 by 5 filters. Now the result is 16 filters, 10 by 10, 16 feature maps with 10 by 10 size. I perform another subsampling resulting in 5 by 5, in this case 16 5 by 5 feature maps. And finally we connect this 16 5 by 5 result. It usually performs what we call flatten operator. Flatten operator will take all those matrices and transform it into a vector. In this case we have 400 values here. So if we just multiply 16 with 5 and 5, 400, and then those 400 values will then serve as input to this fully connected layer. It's a dense layer with 150 neurons, and so on and so forth. And then on the final layers, we have dense or fully connected layers. At least one layer should be dense in order to provide the classes, so the actual class distribution using probabilities. So the output is also dense layer. Each neuron represents a class of the problem. I can have also intermediate dense layers as well, although on more recent architectures, often we have just convolutional, series of convolutions, and sometimes pooling, and just one final dense layer. Often, the first layers are responsible for filtering very low-level features, such as edges, blobs of that means flat regions with colors, specific colors, and then intermediate layers are responsible for finding different texture. As we go near the end of the network, of the layers of the network, those layers are filters that are specialized in specific object parts. And then just the final layer is related to the object classes. So you often say that the first layers are related to low-level and more abstract features, while last layers or top layers are related to semantic filters. And this is useful for us because we want to design a network that is sufficiently deep in order to capture all those nuances of the dataset that we have.